coolest place in the universe.
So I've made a chamber to cool something that's 40 times cooler than space.
Wow. Incredible. Okay. All right, calculus one, we are back. Like I said, at the end of that last lecture, we're back for our last pattern with derivatives, our last general pattern. So let me actually, the first thing I want to do is I want to put up a problem and we'll just kind of look at how we, why we need this new pattern, why we can't use any of our old patterns with a problem like this. And then we'll talk about, I'll do my usual, talk about what that pattern is, and then we'll play it out. Let me also, actually start with, so let me put this problem first. F of x here, this is 17, exercise 17. I guess f of s, but 5x squared plus 3. All right, look at this. In terms of patterns, again, the general patterns we've seen for derivatives, we have pattern for adding and subtracting, which again just means we actually can just take the derivative of each part and bring it down. You have, like I have over here, the product rule and the quotient rule that we just looked at in the last lecture. So we know how to take the derivatives of multiple functions if they're added or subtracted together, if they're multiplied together, or they're divided together. So I want to start with on this one, just kind of asking the question, does this fit any of those scenarios? Do we have two functions that are added together, multiplied, or divided together? What do you guys say? And notice we do have some multiplication here, so we can have -2 times, and we have the square roots, and we do have some addition in here, but notice that this is not kind of a square root function times a polynomial function, right? Or a square root function plus a polynomial function. We do have a polynomial function. Notice that this time it's underneath the square roots. Again, so hopefully that stuck out to you to begin with. So you're looking for compare and contrast. Saying what's different. Yes, you have some operations, but there's a lot different about this. In some sense, there's almost polynomial plugged into a square root function. It's like there was another variable here, maybe an x or a y or whatever, but a y or a z, and you kind of plugged the 5x squared plus 3 into it. So this is not, again, a square root function plus, not square root of x plus 5x squared plus 3 or times 5x squared plus 3 like we saw in the last two sections. It's actually function composition. I won't I won't code it much that way in the way we're gonna look at it, but that's actually what it is, going back to your college algebra classes, function composition. It is 5x² + 3 plugged into a square root function. And so the thing is, again, looking at this, it is a different, so structure wise, it's a different setup. We are not multiplying two functions, dividing them, adding them, subtracting them. So because of that, patterns for those, you can't even convert this really into one of those setups. So the pattern doesn't work. So something like this, where you have one function sort of plugged into another. Fortunately, none of our patterns, none of our general patterns work because we're not adding them, subtracting them, multiplying or dividing. We need a pattern that works for something like this. So, call this the chain rule. That's just a fun name for it, honestly. So I keep using that name. I like that name a lot. So again, aesthetics. We're humans. We're all humans. So need aesthetics, not just logic. So it's a cool name. What the chain rule says, or the pattern that it gives us. So the idea of the chain rule is that saying if you have, so like I said, we sort of have one function, a polynomial plugged into a square root function. So they're saying that the way they're going to write this here is if you have one function plugged into another. So G plugged into F. And you want to take the derivative of this. So, and again, I can tell you the pattern, but I want to give you an idea. I want to do a little more compare and contrast here. I want to give you an idea of maybe difference between what we're about to do and something you've already done. So before I give you the pattern, before we kind of do this problem, I'm gonna, let's say the function was, instead of all that, it was just -2 square root of x. And I wanted you to take the derivative of this. How would you go about taking the derivative of that? In fact, let me give you a second to do that. So actually pause on your side really quick. I'll pause on my side. Go ahead and take the derivative of this, and then we'll kind of talk about what you're doing there. All right. So again, you guys kind of know how to do this. Your y prime. So this is -2 x to the 1/2. And then how did you do the derivative from here? So you multiply by 1/2. It's -1, and then it's x to the -1/2, right? So that's how, this is just the pattern for power functions, right? So now let's think about if I'm trying to take, notice that essentially what I did intentionally was essentially this was the same function, or, it has the same overall form. So the overall structure is the same, -2 times the square root of summana. But now instead of it being x inside, it's 5x² + 3. So essentially what the chain rule says is that we can actually take the derivative of the outside or of the overall structure the same way, but there's a cost. So if I take the derivative of just -2 squared of x, I know how to run this. But by changing x to some function inside, there's a cost to that. And the cost is you need to multiply by the derivative of the function inside. So we're actually going to do the same pattern, the same structure, or the same sort of same way of finding the derivative, but we're going to then include or multiply by the derivative of what's inside, and that's our cost. That's kind of our payment for not having just an x inside that overall structure, that overall function. So again, with the chain rule, what we're saying is one function is plugged inside a larger, a greater function, a greater structure. And so the chain rule says, fine, you can do the derivative of the greater structure, but in order to do that, you got to multiply by the derivative of whatever's inside. That's kind of the way they write this. They say if you want the derivative of f of g of f of gx, I guess, well, Oh no, I think I do want to write it the other way that I was writing it. If you want the derivative of f of gx, then it is the derivative of f with g of x still plugged in. So that's the kicker is again, when we took the derivative here, and an x underneath the square root, and it's you still end up with that x in the end. So we're still going to end up with 5x squared plus 3 underneath the square root. But then I have to multiply by the derivative of what's inside the function. So f prime of g of x times g prime of x. So practically, let me show you how it works here. So what I'm saying is they take the derivative of this. Basically, well, again, kind of the same flow. So first of all, I'm going to rewrite this as -2 and 5x squared plus 3 the 1/2 power. So this 1/2 power, this power function is my overall structure. The 5x squared plus 3 is what's being plugged in. So then when I take the derivative, what I'm going to do is the same thing I would have done if this was x to the 1/2. So I'm going to multiply by 1/2. This means -1. And I'm going to keep the 5x squared plus 3. And I'm going to subtract the power. So all of that stays the same. But now again, the price for you having a 5x squared plus 3 in here instead of an x is I then got to multiply by the derivative of 5x squared plus 3. And what is the derivative of 5x squared plus 3? Working that out, 2 times 5x is 10x, 2 times, 5x is 10x. You're going to multiply by 10x. And so my derivative is negative 10x of x squared plus 3 negative 1/2. And again, we can leave it like that. Or you could rewrite it with the negative power and this and the half sort of rewritten. Rewritten the way they normally would be. So that's going to be a square root on the bottom of the fraction. So negative 10x over the square root of 5x squared plus 3. And that would be the derivative of -2 times the square root of 5x squared. And that's the chain rule. So again, it just says if your overall structure of the problem is not, so again, it's not two functions added, subtracted, it's not two functions multiplied or divided, but it's one function inside of another, then you can take the derivative by doing the overall derivative, the derivative of the overall structure with that inside function still plugged in, but then you got to multiply by the derivative of what's inside. And that's it though. So that again is, we're saying this is one of these general patterns where no matter which functions is plugged into what other function, this is going to work every single time. This is your pattern. Again, just like with the product rule, anytime two functions are multiplied, you use that pattern. With the quotient rule, anytime two functions are divided, you use that pattern. Here with the chain rule, anytime one function is plugged into another pattern and you got your answer. So just like on the last video, let's run a couple more. Let's just kind of practice a couple more of these. And we'll probably do some of those little applied problems, do some second derivatives like we did on the last video. That'll be about it. So let's do another one. I may just make my own. Let's look at something like, let's actually go back to 13. So I want to look at this because, well, this is a good one. Here we have y equals 2x minus 7 cubed. So now looking at this, again, you want to analyze the structure of the function you're trying to take the derivative of. This is a function plugged into another function. This is 2x minus 7 plugged into an overall x cubed structure, power function structure. So then we can take the derivative of this by, we're going to do the overall power function pattern. And we're going to multiply by the derivative of 2x minus 7. So let me actually see if you can do that already. So go ahead and pause on your side. I'll pause on my side. See if you can write the derivative of this out. All right, let's see what you guys got. So again, if this was x cubed, what I would do is I'd multiply down by the 3. Then it would be that thing that x squared. So now it's 2x minus 7 squared. But then we have to multiply by the derivative of 2x minus 7. And what's the derivative of 2x minus 7? That's 2. This is going to end up being 6 times 2x minus 7. You want, you can distribute that out, but this works just as well. It's in factored form. One of the things I want you to notice about this problem, it's kind of a little bit like one of the problems I talked about on the last lecture. On the last lecture I talked about, there was that one problem where it was like you could have just multiplied it out and it would have made it easier. The interesting thing is with chain rule, it's kind of the reverse. Chain rule actually often makes problems easier instead of multiplying them out. Because if you notice, starting what we started with on 13, if you wanted, you could have done 2x minus 7 cubed. You could have done 2x minus 7 times 2x minus 7 times 2x minus 7, worked all that distribution out, combined like terms, and then you could have taken the derivative and you wouldn't have needed chain rule at all. You would just have a bunch of, you would have had a polynomial, a bunch of separate power functions, work the derivatives separately and put your answer down, right? But that would have been a lot of work. Notice how much work this saved you. So the chain rule, unlike product rule or quotient rule, the chain rule actually saves you work when otherwise you could have multiplied something out. So we got this pretty darn quick without having to worry about a ton of distribution and combining like terms. So that's just kind of a note. That's why I wanted to bring up this question. Let's look at some problems with just, let's do my usual thing. Let's throw in some other functions. Let me make up some of my own problems then, because once I not gonna be what I want them to be for y'all. All right, so we did something like that. We did something. do maybe this, let's do the tangent of maybe cubed minus 4. Something like that. So my function is tangent of x cubed minus 4x, and I want you to take the derivative. So when you're looking at this again, the first thing you want to identify is which function is being plugged into what function. And what do you see here? What's being plugged into what? X cubed minus 4x, that polynomial is being plugged into a tangent. So tangent's your overall structure, that's the overall derivative you're going to take. Then we got to multiply by the derivative of x cubed minus 4x. So let's see if you can play that out. Go ahead and pause on your side, I'll pause on my side. All right. So what is the derivative of tangent? The derivative of tangent is secant squared. So we're going to put secant squared of that x cubed minus 4x. Then we have to multiply by the derivative of x cubed minus 4x. And what did you guys get for that? That's going to be 3x squared minus 4. And don't have to write it this way. I'm going to write it actually with the 3x squared minus 4 in front of the secant, just so visually I don't confuse. I don't think I'm doing secant squared of all of this. So it's just basically being clear that 3x squared minus 4 is in some sense the coefficient in front of the secant squared. Good. That's easy enough. And honestly, that's all it's ever going to be. Actually, let me give you guys a couple more to just run them on your own. Sorry, let's make this y equals. Well, let's do those for now. All right, so I'll give you again pause on your side. I'll pause on my side. Let me move the camera too. You guys can't see those, so let's do that first. Ahead and just two. So let's see what you get for the derivatives. All right, so let's see where you guys got here. So 4 is interesting. So 4 is, again, you want to figure out what's being plugged in and what's your overall structure or your outside structure. So notice on 4, Our overall structure is actually an e is an exponential function, e to a power, e to x. What's being plugged in is the 4x squared minus 3x, so that's being plugged in as the power. So then when I take the derivative, my overall structure is e to the x, so what's, or e to the something, so what's the derivative of e to the x? Just e to the x, so my overall derivative, or the derivative on the overall, the outside structure, it's just the same, e to the 4x squared minus 3x. But then we have to multiply by the derivative of 4x squared minus 3x, and what did you get for that? That's 8x. And that's our answer. Then there's really nothing we can do there. We can't really multiply those pieces together. Alright, now on 5, again, what's your overall structure? What are you plugging in? Your overall structure is basically a natural log of x. You're plugging in secant of x. So then on the derivative, what is the derivative of natural log of x? Good, it's 1 over x. So it's 1 over secant x. Then we got to multiply by the derivative of secant x. And what's the derivative of secant x? Good. That is secant x tan x. I actually noticed that your secants cancel. So what are we left with here? Just plain old tan x. So the derivative of natural log of secant x is tan x. All right. And then, so this kind of is, again, just like the last couple patterns, you're just mixing and matching functions, right? So beyond this, you might have some problems. Let me pull up some other problems. Do something like this, maybe sine. Oh, sine squared. So y is going to be sine squared. E squared plus 6. Sine squared of x squared plus 6. I want to take the derivative. So again, we want to kind of analyze, we want to figure out what's my overall structure and what's being plugged in. What would you guys say on this? And so it seems pretty obvious, or at least you can see pretty easily x squared plus 6 is being plugged into sine. But notice by having this squared here, what I really have, so I actually have that sine then, including the x squared plus 6 being plugged into an even larger function. So this is actually essentially one function plugged into another, plugged into another. So just I'll show this with parentheses. What we have here is really sine. So it's x squared plus 6 being plugged into sine, but then that thing is being plugged into a squared function. Like it's an x squared. So we kind of have, again, function within function within function. And that's completely plausible. So me making up this, I'm not just making up some weird thing outside of the norm of what you might see, again, in engineering, science, physics, chemistry class. I mean, this is decently normal. So it is function within function within function. So in order to take the derivative of this, in some sense, you'll see what we're going to do is we're essentially going to do chain rule within the chain rule. We're going to sort of do chain rule twice, but you really want to think of it as we're doing chain rule within chain rule. So my largest structure is the squared structure. Blah, blah, blah squared. So when I take the derivative of this, first going to start, so the derivative is first going to be 2 times all of that thing. Now, so chain rule says you take your largest structure, your largest pattern. So it's going to be 2 times this thing. And then we have to multiply by the derivative of this thing. And to do the derivative of this thing, we have to do chain rule again because we have an x squared plus 6 inside of a sine. So we almost have to do that derivative kind of, we can do it on the side, do that derivative by itself or separately. Once we have that derivative, that then becomes what we multiply by. To do this derivative, we have to do chain rule again. We have x squared plus 6 plugged into a sine. The overall structure on that is sine, and what's the derivative of sine? Sine is cosine. That's gonna be cosine of x squared plus 6. Then I need to multiply this by the derivative of x squared plus 6. What's the derivative of x squared plus 6? That's 2x. But again, this is just the derivative of the sine x squared plus 6, which is the thing plugged into the squared. So now I'm just gonna shove this over here. I'm gonna multiply this by all of that. So I end up with times cosine x squared plus 6 is 2x. We can do a little rearranging there. This is 4x sine x squared plus 6 cosine x squared plus 6. And that's actually good. There's actually a trig identity, a double angle identity that allows us, we can actually simplify this farther. I don't think the book is asking for that in its answers. Just to play with it. So if you remember your double angle identity, one of your double angle identities says that sine of twice an angle equals 2 times sine of the angle times cosine of the angle. But notice we kind of have 2 times sine of an angle, cosine of an angle. So we basically could rewrite that part. So basically I'll factor out a 2 here. That leaves me with 2x. And then I can rewrite the rest of this part is sine of double whatever this is. You get natural sine of 2x squared plus 12. This is meaningfully simpler though, so if you write it this way, so this is also accurate, this is also correct. But anyway, derivative of sine squared x plus 6 is 2x sine squared plus 12. So you might have problems like this where it's essentially, again, not just a function inside a function, it's a function inside a function inside a function. You could keep doing this, by the way, kind of expanding almost like a Russian nesting doll, kind of keep expanding out. As long as you can keep track of the chain rules that you're doing, kind of in one function inside of another, then you get the answer fine. So let me give you one like this just to play with. Do crazy and large. Let's do of X. E. I think let's do something like this. So E. Give me a second. I think there was another. Well. Yeah, no, did. Something like this, E to the square root of cosine X. Good. So again, kind of function within function, but that's within a larger function, the E to the X function. So let's see if you can work that one through. Thoughts on your side, no thoughts on my side. Let's see how you made it on this one. So again, you don't have to do this extra drawing that I'm doing, but you do. But you can kind of imagine this is, so again, this is E to the square root with cosine X in the middle there. My overall structure is E to the X. So when I go to take my derivative, it's gonna be E to whatever is there. Right? So it's gonna be E to the X, it's gonna be E to the square root of cosine X. Then I gotta multiply this by the derivative of cosine square root of cosine X, which itself is gonna require chain rule. So the square root of cosine, for the square root of cosine X, what's my overall structure? It's a square root or X to the 1/2 power. In fact, well, that's the way I'll write it here. Help us emphasize the point. So it's a power function. So then my derivatives for power functions are 1/2. Multiply it, sorry, so I just multiply it by 1/2 and subtract the power. It's gonna be 1/2. Sine X to the negative 1/2. Then I have to multiply that by the derivative of cosine X, and what's the derivative of cosine X? That's a negative sine X. Again, it's kind of overall derivative, multiplied by the derivative of the next part, times finally the derivative of the inside. And then you can try to simplify this as much as possible. This is kind of an interesting one because yeah, there's just a lot of pieces that in the end are not really gonna mesh well with each other. We got e to the square root of cosine x up top. You've got, and actually, so that's gonna be times a negative times sine x. So actually, let me rearrange this. It's gonna be negative sine x e to the square root of cosine x over 2, and then you're gonna have the square root of cosine x on the bottom there. That is our derivative. It's a mess, but it is true and it is there. All right. And especially for this section, that's about as crazy as chain rule is gonna get. It's getting late on my side. I was trying to get another video in today. I'm see I may not be able to do that. But either way, so there are some problems. There are some problems in this section where they want you to find the equation of the tangent line, and they want you to find, you know, what point or what x value where the tangent line is horizontal. You guys can do those. So I think the only other thing I'm concerned about showing you really quick or just doing an example problem with is just like the last section, they're going to go through and ask you to find the second derivative of things. So let's look at one or two of those. There's our did a um do something like this is 125. Problem 125, section 8, or sorry, 3.4. For 125, so again, they want you to find the second derivative. But my function here is gonna be sine of x squared. So inside my sine is an x squared. So looking at this, so again, you're finding the second derivative, so you just know kind of how to play this out. And let me make sure you guys. You guys can't. Um. So, but you know how this, the overall process here, you're gonna find the first derivative, get a result for that, and then you're gonna find a derivative of that, and that'll be your second derivative. All right. Now for the first derivative here, again, notice that this is not sine of x times x squared, this is x squared in a sine function. So this is chain rule. So let's practice chain rule. Go ahead and pause on your side, I'll pause on my side. Go ahead and figure out the first derivative here. All right, sweet. So x squared is within a sine. So the overall structure is sine, and what's the derivative of sine? That's cosine. So y prime is going to be cosine of x squared. Then we need to multiply by the derivative of x squared, and what is that? That's 2x. So I'll just rewrite this this order, so I'm not confused about what we're taking cosine of. 2x cosine of x squared. Now you want to take the derivative of that. And to take the derivative of that, so I want you to look at that for a second and kind of shout at the screen, so what patterns of derivatives are we going to need there? Just kind of what do you see? So notice that kind of like we began with, we do have a function within a function. We have x squared within cosine. And we also just have this times 2x there. So in some sense, what we're gonna have to do with this is overall, we're doing product rule because we have 2x, we have one function times another. But when we find the derivative of the cosine of x squared, we're actually gonna have to use chain rule, to find that derivative. We're kind of doing two patterns in one, or at least one within the other. So overall, so largest, the largest we can look, this is one function to another. So we need to start by doing product rule. So that means we're going to do 2x times the derivative of cosine squared. I'm going to leave that kind of undone right now. And then plus, what's this other part going to be? First function times derivative second plus second times the derivative of the first. So cosine of x squared. And then what's the derivative of 2x? Times 2. So overall, this is product rule. But now to do this derivative, you're going to have to go through and you can almost do this as side work. On its own, you got to do on your own, or on its own, you got to find the derivative of cosine of x squared. So that's actually what I'll kind of challenge you guys to do. So go ahead and do your own little side work here, or you can do it in the main flow of the problem. But figure out the derivative of cosine x squared, plug that in, and then see if you can simplify it from there. So go ahead and pause and work on that. All right. So doing this derivative, and again, like I said, you can do this wherever you want. When I was in middle school and then high school for 3 years in a row, my dad took me to, so I grew up in Florida. You guys don't have Waffle House here, but Waffle House is best breakfast place ever. My dad would take me every morning. He had a pretty early job. I had pretty early classes. So he'd take me every morning and we get coffee basically in the morning. So he'd take me there and we'd talk or whatever. A lot of times we would like talk about science or math and, so the fun thing was we'd sit there, we'd be working on something, some problem, and we'd just take napkins, right? And just work out the little bits on there and kind of take that result and plug it into the main thing we were talking about or what we were thinking. So that's sort of every time I do side work, that's actually what I imagine. Imagine being at Waffle House with a cup of coffee, just little square napkin on the side, just working out stuff. So the little side work here, I need to find the derivative of cosine x. And cosine x squared is x squared plugged into a cosine function. So overall, I'm taking the derivative of cosine function. What's the derivative of cosine? That's negative sine. So that's going to be negative sine of x squared. Then what's the derivative of x squared? So then I got to multiply my cost of not having an x there. I'm going to multiply by its derivative. So what's the derivative of x squared? That's 2x. Overall, we're going to have basically negative 2x sine of x squared. So let me plug that in. So 2x times negative 2x sine x squared. Now I'm going to have what? Plus 2 cosine of x squared. And do a little multiplication there. So we end up with, and I'm going to put my positive part first. So 2 cosine of x squared minus 4x squared sine of x squared. And maybe you can factor out a 2. I don't see any trig. I can't think of any trig identities that'll help us here. So this is probably about where that ends. That'll be the second derivative. There you go. So again, just, the overall, whatever section we're in, whatever function you're looking at, finding the second derivative, the overall play is the same. Find the first derivative, and then take that and find the derivative of that. Especially, I mean, really when you're dealing, especially with chain rule and product rule, after that first derivative, you're gonna have many pieces there. And so you're likely gonna have to then do, when you find your second derivative, you're not gonna have to do one pattern of derivatives, but probably a couple patterns. Because you're gonna have pieces multiplied like this. Or you're basically gonna have pieces multiplied. So. But otherwise, that'll get you through this section. And that'll actually get you through the end of this chapter and the end of basically finding, like I said, almost the end of finding derivatives. So we'll see in a couple sections in the future, some kind of corner cases and different smaller cases of derivatives that maybe don't use these patterns, and we'll talk about how to do those. But otherwise, this actually kind of covers everything. We can pretty much take the derivative of anything at this point. Okay, so dig into that, finish that work for the weekend, and then again, going into next week, we're gonna have the midterm on Thursday, so I will have a review. Actually, I already have a review, and I will have a video for that review up hopefully by Monday night. So you can probably watch that starting about Tuesday. So you have Tuesday and Wednesday to kind of look at that review. When you're watching the review, as it kind of says on the review page that you're going to see in next week's module, the key is not to memorize things. You kind of see as you're working through these problems, right? So depending on which functions I throw together and how I throw them together, not only is your pattern for getting through it different, but algebra that you're doing out of that is wildly different. So the thing is, you shouldn't be thinking, oh crap, I got to memorize all that, because you don't have to memorize all that. It's impossible to memorize all that. Two, you actually don't need to. So you guys have the algebraic technique you need. You have the pre-cal knowledge and technique that you need. And now you have the not only the knowledge, but the patterns with derivatives that you need. You got to rely on those as a tool. Just kind of critically think your way through the problems, and I promise you're going to get it. So when you're looking at that review and you're watching me go over it on the video, just make sure don't memorize how to do that problem. Make sure that you understand why I'm doing the steps that I'm doing. And if you've got that, that's actually the cool part of it, is I can't throw a problem at you that you can't do, because you're majoring on how and why you're getting through the problem, not what the problem is and memorizing these little things. I promise you, if you major on how and why you get through a problem, I cannot write a problem that you can't do. I'm not saying that to be nice or to be buttery as a teacher. I literally, logically, I cannot write a problem you can't do. So that's what you got to trust. Make sure you understand how and why on all those problems that I do on the review, and then relax, because I can't write a problem you can't do. So you can look at that Tuesday and Wednesday of next week. And then Thursday, you'll be zooming in for the final. I'll be sending out a message, not tonight because because I'm still making these videos, but tomorrow I'll be sending out a message with the time slots for next Thursday, and you guys can start responding to that with when you can zoom in. So anyways, in that message, you'll get details about that. All right, good stuff. I will see you guys next week.